Hello everyone. Welcome to the SWAM NPTEL course on engineering aspects of biofuels and biomass conversion technologies. I am Professor Ijaz Ahmed, currently Assistant Professor in the Department of Chemical Engineering at IIT ISM Dhanbad. In Module 3, we were discussing earlier about the briquetting and pelletization. And in Lecture 1, if you remember, we discussed about the briquetting. In Lecture 2, also we will continue with the briquetting part. So if you remember, in the previous class, we discussed about the briquetting of biomass and how to develop a process flow diagram for biomass briquetting. However, due to shortage of the time in the previous class, we will continue with this and we couldn't discuss last time each and every step. So in this class, we will discuss the each and every step of the biomass briquetting, particularly sorting, cleaning, drying, size reduction, preparation and densification. All these parts we will understand in detail. So if I say here the overall briquetting process, so it primarily consists of sourcing the biomass feedstock and then pre-processing it and then subjecting it to densification. Now this densification involves application of pressure, heat and binding agent. Okay. Now why do we need it? Of course, we don't want to lose the biomass residue. Okay. We want it to hold it together. Okay. So this is needed to convert into the briquettes. Now these briquettes are compacted forms of organic waste materials which are utilized for both household and industrial energy applications across rural areas as well as the urban areas. The physical characteristic of briquettes are such as, of course, the quality, size and shape depends on the type of raw material. Like here you see different types of biomass. So it will depend on so I would say the physical characteristic of briquettes will depend on the raw material, the mold design and the technology which has been used. Like I showed you 3-4 technologies in the previous slide. Okay. However, in most of the cases, you will see that the briquettes are produced in cylindrical form, okay, which have a typical diameter 25 to 100 mm, while the length is from 10 to 400 mm. Besides that, the other shapes, for example, the square, rectangular, polygonal forms are also produced. So, if you see the briquettes, they can be of different shape and size, but in most of the cases, you will see that they are in cylindrical form and typically in a diameter range of 25 to 100 millimeters and the length 10 to 400 millimeter, depending on the manufacturer and the end user or the buyer. Now, these densified biomass like briquettes we are discussing here offers several advantages that include, of course, the high energy density, the enhanced energy content and easier handling and transportation. This is very important. If you remember, we started from the challenge with the transportation of biomass, and that's why we said that we need to densify this powder form of the biomass. Otherwise, one truck will hardly take few tons of powder biomass, and if we convert to pellet or the briquette, it will take several tons of the biomass. So we'll be, if we transport in the powder form, we'll be having huge economic losses. So the advantages including the enhanced energy content, easier handling and transportation. Besides that, once you have pellets formed, the storage also becomes easier. So you can imagine that storing powder biomass will require more space than storing the briquettes and the pelletized biomass. And because here we are also removing the light volatile material, the combustion properties will be better and particulate matters emission will reduce. The reason is because now there are no more powder, rather than it is in solid form, and all of these will be in of similar shape and size and density. So if we say that energy content per kg of biomass is this. For most of the briquettes, we can say the energy content of the my briquettes will be this. It will not be varying because mostly shape and size and density is similar for all kind of briquettes. So as I said in the beginning that this is the overall process. But if we look at these all sub processes like processing, pre-processing, I would say, pre-processing, drying, size reduction, preparation and densification, all are very important. Particularly, I will start with pre-processing, which is of course sorting and cleaning. So once we take the biomass, the biomass is often dumped somewhere, or if it is coming from the agro residue or the forest residue or from any source, it is likely to have some dust with it, some other inorganic materials and unwanted materials in it. So first step we do is the sorting and cleaning. The cleaning followed by, of course, if we have to clean the biomass, if we have to remove the dust, we can sieve it. So one way is sieving for the cleaning. So in this, I would say rather the briquetting process begins with the sieving or cleaning of the biomass. And what we do, we sort out different kind of biomass to ensure the uniformity in size and quality. Now this is achieved via the sieving, which is carried out to eliminate the contaminants, particularly the non-biomass particles, so that we can process the material further. Now if you see here, if we don't remove the dust or contaminants or non-biomass particles, what will happen? There will be more load on drying. There will be more load on size reduction, and eventually if it comes here, get transferred to this final end product, what will happen is the weight will be high while the energy density will be less because it will have some dust and other materials. So it is very important that sorting and cleaning should be done after collection of the biomass. Now once the biomass is cleaned, sorted and cleaned, then we have to dry it. Now why we dry it? We can do the drying after sizing also. So again, as I said, there are different ways. So you can put a drying unit here, you can put drying here, or you can put drying here. So anyway, you can do size reduction first or you can do drying first. But if we look at why drying is required, okay, so we have different types of biomass. For example, coffee husk, groundnut shell, rice husk. These are mostly dry. They may not require that intense drying because usually they get dry naturally. However, there are other kind of biomass which may have high moisture content, as I said in the beginning, that it can go up to 80%. So that has to be removed. The moisture has to be removed because it enhances the efficiency of briquetting by reducing the moisture, and when moisture is removed, so the biomass weight will be more. Otherwise, if 80% moisture is there, 80% weight is from the moisture. However, we don't do complete drying. The reason is a small amount of moisture is very important and very beneficial for interparticle adhesion. So in nutshell, if I say drying is very crucial step, especially for feedstock with high moisture content. In some cases, we may not require, as I said, like coffee husk, groundnut shell or rice husk. But in most of the cases, drying is very, very important in order to remove the moisture from it. However, we don't remove the 100% moisture. We keep some moisture into it so that it will help us in adhesion of the particles to make the briquettes solid. Now this stage is energy intensive because we are drying, and I said like drying has around sometimes biomass has 40 to 80% moisture. Now you imagine if you have to remove 40 to 80% moisture, how much energy will be required. So in the whole unit of briquetting unit, if you look at, drying is one of the most energy intensive units. which accounts for almost 70% of the total energy consumption in briquetting process. So if you have, let's say, coffee husk, if you are getting coffee husk, groundnut shell or rice husk, even at a 1 rupee higher cost, your drying requirement will reduce, and then eventually you will be making profit out of that. So this is also one trade-off between that what kind of biomass with what percentage of moisture I should buy, so that my processing part and drying part becomes easier and less costly or less expensive. Now usually the ideal moisture content in the biomass should be between 5 to 15% for optimum densification. Now as I said, because we cannot remove the whole 80% of the moisture. It is required, if you look here, it is required for interparticle adhesion. So usually how much moisture should be there? Then it depends again on type of biomass, but if I take a range, typically it is between 5 to 15%. In some cases it would be 5%, in some cases the requirement would be of 15%. Now after this we go to size reduction. However, you can also do size reduction prior to drying. Either way, it is depending on if we make an economic trade-off, we will have to see that where we are making more profit. So that is again detailed engineering part. But it's not necessary that you will have size reduction part only after drying. You can have first size reduction, then drying. But one thing remains fixed, that you need both drying as well as the size reduction units. Particularly you need choppers, you need grinders, shredders, and then sieving unit, of course, because you need the uniformity in size. So if I talk about size reduction, it enhances the surface area, as I told you in the beginning, and also degrades lignin in partial manner. Now lignin is a binder which holds the cellulose and hemicellulose together. Okay. So if it degrades lignin, it improves the mechanical bonding between the particles. Similarly, you can use either a chopper or a grinder or shredding or sieving. Besides that, there are several other equipments used for size reduction, that includes hammer mills, knife mills, disc attrition mills, and linear knife grids. Now these all are to decrease the size. Out of this, the hammer mills are widely regarded as most effective, followed by cutting mills. The reason is, of course, one is the uniformity in size, we get better, and the second is related with the power requirement and the simplicity. Hammer mills are very simple to operate, and that's why they are most widely used. However, there can be other mechanisms as well. You can have electronic automated shredders, you can have automatic grinders, you can have choppers. There are several other things possible. However, for finally going to the powder form, hammer mill is one of the best options. Now the overall target for, as I said, reducing the particle size is to increase the surface area, which is very important step before densification. Okay, so densification is happening here, but you need this in order to reach this stage. After that, as I said, we need different binders. So if you look at in the previous slide here, what we discussed in one of the slides here, what we discussed was about the binders, and in most of the cases you will see the binders were required. Now we will go to why binders are required. If you look at, so one thing is definitely the adhesion. Okay, they are very important for making the adhesion between the interparticle adhesion, like some part of moisture is required. Similarly, the binders are introduced during the feedstock mixing phase or post carbonization, but they should be fed before the briquetting part. So if you will see here, we add the binder and then we have a mixer. What we do, so from here we took the biomass, we sorted, we cleaned, then we dried, we reduced it to powder form, and then we brought that biomass here and added with the binder. Now when we are adding for a uniformity of the binder distribution, mixing is very important. If we don't mix it properly, the binder may not be distributed uniformly. And if it is not distributed uniformly, then the binding of the materials will become difficult at all the places. At some places it will be very good, at some places it may not be good because the binder is not available in sufficient amount. So these two steps are very important, particularly where the low pressure compaction is used. Binders are very essential. So we'll discuss also about the effect of pressure. So you can say there are high pressure compaction and there are low pressure compaction. They are both. So low or we can have high. So right now we are discussing about the low pressure. So especially wherever we have low pressure compaction, the binders are very essential because they help in binding, and then there are some kind of biomass which do not aggregates naturally. So you need something to aggregate them. The binder addition, as it is mean to, it enhances the densification efficiency, mechanical integrity, as well as the combustion properties of the final product. Now, if you recall again, what we are using as a binder, starch, paper, lignin, these all are again combustible materials. So they improve the combustion property of the final product. Besides that, the use of binder doesn't only help in briquettes, but they also help in minimizing the equipment's wear and tear. Because when there is a improved cohesion, when there is a improved cohesion between the feedstock, the wear and tear of the equipment will reduce. So the binding and mixing are very important. For example, the binders facilitate the interparticle connections as well as they make the powder they enable the powder to get converted into the briquettes by holding them tightly together. Okay, that is called interparticle connections. Similarly, there are different types of binder which are used, but before moving to that, I would say, like I was saying, that the binder facilitates a strong interparticle connections, thereby acting as a matrix for a stable briquette formation. And the binders again are, as I said in the beginning, that there could be several type of binders. If we primarily classify them, there can be inorganic binders such as clay, limestone, etc. that you saw in the example that we discussed. We can have organic binders. So one is inorganic binder. We can have organic binders which are further subdivided into biomass based. For example, you saw the cassava starch, molasses, cow dung, pulp waste, etc. Or we can have a binder which is tar and petroleum based. For example, we have bitumen, we have pitch, we have lignosulfates, we have polymers. In addition to it, we have compound binders which are combination of organic and inorganic materials to optimize the performance. When we say performance, the binding performance or improve the efficiency of the strength of the briquette. After this stage, what happens that once now what we did, if you recall it, we started with the biomass, we sorted out, we cleaned, then we dried. Now we did the size reduction part. Here we got in powder form or you can say reduced size in few millimeters or microns, and that powder is now mixed with the binder. Binder is added, charged into it, and then mixed it properly. So we safely assume, let's assume here that now the binder is uniformly distributed. So what you have here is, so here you have only powder form of biomass. Now here the powder form of binder and biomass mixture, but still it is in powder form because binder itself cannot bring something together and make them compact. What we require is to make them compact and densify it. So we have densification process. Now in densification process again, there are different steps that we have to follow. So if I start with, it is like I said in the beginning, briquetting is solid biomass upgradation technique that converts loose low density material into compact energy dense fuel with uniform characteristic. Now then if I have to compact something, obviously you need a mechanical pressure. Therefore, the briquetting involves the applying mechanical pressure to compress the loose biomass into a compact form. And when we compact the loose biomass, then we are reducing its volume and forming a stable cohesive product that retains its shape after the compression. Okay. Now, as I said, the compaction pressure is very important. For example, if we have a low compaction process, then we definitely require a binder. But in some cases where high compaction pressure is used, we may not require binder. So compaction pressure has a very important role that it plays during the briquetting of the biomass. Particularly, as I said, like biomass densification can be performed under either high or low compaction pressure. Now, the selection of the compaction pressure level depends on several factors, and that factors is first definitely is the type of biomass. So here, if you have let's say woody biomass, so if you have let's say woody biomass, you have bagasse or powder biomass, you have aquatic biomass, you have municipal solid waste biomass, or depending on what kind of biomass you have, their interaction or interparticle interaction will vary. So I can say safely that the compaction of those biomass particle depends on the type of biomass. Therefore, the selection of compaction pressure also depends on the type of biomass feedstock. Now the second is definitely it depends on the moisture content. As I said, if you see the moisture range was typically from 5 to 15%. 5 to 15%. In some cases, for some of the biomass, the 5% moisture content is good enough to hold them tightly, while in some cases up to 15% moisture content is required. Besides that, particle size and geometry is very important. When compaction happens, so it's not just cohesive forces or interparticle forces that hold the biomass together, but also the locking of the different shape and sizes. So for example, if I have, let's say, my shape of my biomass is like this, and then I have another biomass which has shape like this. Okay, if I compact them hard, so what will happen? It will go something like this, and this will come in here. Now taking them out will become very difficult. So the shape and size plays very important role, and when we say the particle size as well as the geometry, which of course is dependent on the shape, which is a shape factor. So the shape and size of the biomass is very very crucial for deciding the compaction pressure. Now usually low pressure compaction, as we discussed earlier, requires the addition of binders. Okay, because we are not pressing it too much hard so that they can bind them, and because of the shape and size they can get entangled. So there we definitely require binder to enhance the particle cohesion. While for high pressure briquetting, usually the natural binding agents like lignin, starch, proteins and pectin are present in the biomass. Okay, so what happens when we apply the high pressure, they get activated, okay, and released under the pressure. And when you remember, when we looked, lignin itself is a binder, starch is a binder, protein is binder, pectin is binder. all we have discussed earlier. Now they are the part of biomass. So when we apply the high pressure, if they are getting released under the pressure, they will eventually start promoting the effective interparticle bonding without external binders. That's why if you look at in some of the cases, for some of the feedstock, we actually did not require any kind of binders in the table that I showed earlier. Okay. Now, besides the pressure, there is a role of temperature as well, because in some cases we use carbonization furnace or heating. You can say, when I show that what kind of briquetting machines are there, you will see that in some cases there are screws, screw conveyors, some cases there are carbonization furnaces, some cases there are heated screws. So if we don't use the carbonization furnace, we will get briquettes like this, which we call as woody briquettes or similar to wood. While if we use carbonization furnace or heating, we will use this kind of briquettes, which is mostly like charcoal. Now, what carbonization furnace does? So what we are doing in the carbonization furnace? We are increasing the temperature. That means eventually the property of my briquette also depends on the temperature. Particularly, the temperature enhances both the biomass feedstock as well as the briquetting. For example, dye before or during the process. If the dye temperature is excessively high, it reduces the friction between the biomass and the dye wall, and that allowed densification at lower pressure. But then when you make the briquettes at lower pressure, that will result in briquettes of lower quality or inferior quality. The reason is, now the energy density and the density, mass density, will be lower. So that will result in the inferior quality of briquette. Whereas in case of lower dye temperature, increases the required compaction pressure. And when compaction pressure is increased in the compression pressure is required, then energy input, more energy input will be required. And when more energy input is required, that will potentially slow down the production rate. But in this case, we will have higher quality briquettes due to a stronger internal bond. Again, it depends on where we are putting the carbonization furnace. Sometimes we put before this, sometimes we put after this. But anyway, briquetting can be in this form or briquettes can be in this form. Now, as I said, if you remember, the binders has a very important role. I discussed. So, what actually binders does and what kind of forces acts while we are making the briquettes? What kind of forces acts in a briquette? So, these are like, for example, the binding, briquetting, and the extrusion are both methods of compaction. Okay, which involve the compression of particulate matter within a confined space. When fine particles or the biomass, the powder biomass that can deform under the high pressure are compacted, the external binders may not be required. But in most of the cases, you will require the binders, and the mechanical integrity of such compacts is typically due to the van der Waals forces where you are not using a binder. So particularly when I said here the example that they may not require, so here this, when dye temperature is excessively high, or you can say when we have the pressure impact, yeah, so the low pressure compaction, the addition of binder is necessary, while for high pressure the binder is not required. When binder is not there, then what kind of forces acts? So these are the forces that acts, particularly the van der Waals force, the valence electrostatic interactions, the mechanical interlocking of the particle which I explained to you, and then there are several other possibilities. And now these all are usually, these are non-binder forces. These are non-binder forces. So while binders make some sort of weak chemical interactions, the without the use of binders, the what you can say van der Waals forces are primarily responsible and the interlocking of the particles because of, you see here, this particle could have been of this shape, and now this particle of this shape comes here and you compress it together, then they'll get locked, and then taking them out will become difficult. So interlocking of the particles is one of the important factors. The electrostatic forces are very important because when you are giving high compression, and if there are interparticle electrostatic forces, they will attract each other and try to hold the particles together. Similarly, the molecular forces that include the van der Waals forces, they are very important. If we use binders, then there are hardening binders which follows a phenomena similar to that of the adsorption. Okay. Particularly under high pressure, the natural binding components present in the biomass like lignin, starch, as I said, may become active, and when they become active, they will lead to the improved particle cohesion, and then the binding strength will improve. However, there are some materials even at higher pressure also where you will require additional binders which are very necessary to achieve the sufficient strength even with the high pressure. So as I said, in most of the cases for high pressure you don't require a binder. That's a thumb rule, but it's not a law. That means in most of the cases, let's say 90% cases, you will not require a binder, but then there will be 10% cases where you will require addition of a binder even in high pressure compaction. So with this, I would like to end today's class here and see you in the next class. Thank you.